Welcome. Today we're going to walk through a practical engineering problem: how to determine the orifice diameter needed to allow 1800 liters per minute of water to flow through, given a pressure drop of 1.5 bar. This is a common challenge in fluid mechanics and is essential for designing piping systems, water treatment plants, and more. We'll break down the process step by step, using clear calculations and logical reasoning. By the end, you'll see how each piece fits together to reach the final answer. Let's get started with the basics and set up our goal for this calculation. Before diving into calculations, let's clarify what we're trying to solve. Our goal is to find the diameter of an orifice that will let 1800 liters per minute of water pass through, with a pressure drop of 1.5 bar across the orifice. This means we need to relate flow rate, pressure, and the physical size of the opening. To do this, we use standard fluid mechanics equations and convert all our units to the SI system for consistency. Now let's move on to the first step, converting the flow rate. Flow rate is given as 1800 liters per minute, but for our calculations we need it in cubic meters per second. Since 1 cubic meter equals 1000 liters, and there are 60 seconds in a minute, we divide 1800 by 1000 and then by 60. This gives us a flow rate of 0.03 cubic meters per second. This conversion is crucial because all our subsequent calculations will use SI units. With this value in hand, we're ready to move on to the next step, converting the pressure drop. Next, we need to convert the pressure drop from bar to pascals, the SI unit for pressure. We're given a pressure drop of 1.5 bar. Since 1 bar equals 100,000 pascals, we multiply 1.5 by 100,000 to get 150,000 pascals. This step ensures that all our units are compatible for the formulas we'll use later. Now, with both the flow rate and pressure in the correct units, we can proceed to consider the properties of the fluid itself. Accurate calculations: we need to know the density of water. At room temperature, water has a density of about 998 kilograms per cubic meter. This value is standard and widely used in engineering calculations. Knowing the density allows us to relate pressure and velocity in the next steps. With flow rate, pressure, and density all set, we're ready to calculate how fast the water will move through the orifice. Now let's find the velocity of water as it passes through the orifice. We use the formula V equals the square root of 2 times the pressure drop divided by the density. Plugging in our values, that's the square root of 2 times 150,000 divided by 998. This works out to a velocity of about 17.34 meters per second. This velocity tells us how quickly the water will jet through the opening, which is key for determining the required area. Connect flow rate, velocity, and area. We use the orifice flow equation. Q equals seed times the square root of 2 delta slash rho. Here, seed is the discharge coefficient, which accounts for real-world effects and is typically around 0.62. We rearrange the formula to solve for the area. This step is crucial because it links the physical size of the orifice to the flow and pressure conditions we've already calculated. Let's rearrange the orifice flow equation to solve for the area. The formula becomes A equals Q divided by seed times the square root of 2 delta slash rho. We already have all the values. Q is 0.03 m3s, seed is 0.62, and the velocity from before is 17.34 ms. Multiplying seed by velocity gives us the denominator, and dividing the flow rate by this result gives us the area needed for the orifice. Now let's plug in the numbers. The denominator is 0.62 times 17.34, which equals about 10.75. Dividing the flow rate 0.03 by 10.75 gives us an area of approximately 0.00279 square meters. This is the cross-sectional area the water needs to flow through at the given velocity and pressure drop. Next, we'll use this area to find the diameter of the orifice. The area we just calculated is for a circular orifice. To find the diameter, we use the formula for the area of a circle. A equals pi times d squared divided by 4. Rearranging d equals the square root of 4a divided by pi. Plugging in our area, we get d equals the square root of 4 times 0.00279 divided by 3.1416, which gives us a diameter in meters. This step translates our calculated area into a real-world measurement. Substitute the numbers. 4 times the area is 0.01116, and dividing by pi gives about 0.00355. Taking the square root of this value, we get a diameter of approximately 0.0596 meters. This is the size of the orifice needed to achieve our flow and pressure requirements. For practical use, it's often helpful to convert this to millimeters. Make the result more practical, we convert the diameter from meters to millimeters. Since 1 meter equals 1000 millimeters, we multiply 0.0596 by 1000, giving us 59.6 millimeters. This is the final orifice diameter required for our system. Rounding to the nearest whole number, we get about 60 millimeters, which is a standard size for many applications. Let's quickly recap the steps in a summary table. First, we converted the flow rate to 0.03 m3s. Next, we converted the pressure drop to 150,000 pascals. Used the standard water density of 998 kg/m3, calculated the jet velocity as 17.34 ms, found the required area as 0.00354 m2, and finally converted that area to a diameter of 59.6 m. Each step built on the previous one, leading us logically to the answer. In one sentence, we calculate how fast the water goes through the plate from the pressure drop, then find how big the hole must be. This approach is fundamental in fluid mechanics and helps engineers design safe and efficient systems. Understanding the relationship between pressure, flow, and orifice size is key for many real-world applications. Discharge coefficient, seed, is a crucial factor in the orifice flow equation. It accounts for real-world effects like friction and turbulence that reduce the actual flow compared to the ideal case. For sharp-edged orifices, a typical value is 0.62. Using the correct seed ensures that our calculations reflect what will happen in practice, not just in theory. Sizing orifices is not just a textbook exercise. It's used in designing water distribution systems, industrial processes, irrigation, and even in household plumbing. Understanding how to calculate the right size ensures efficient operation and prevents issues like excessive pressure loss or inadequate flow. If the pressure drop across the orifice changes, the required diameter will also change. Higher pressure allows for a smaller orifice for the same flow, while lower pressure requires a larger opening. This is why it's important to use accurate, real-world values when designing systems. If you're working with a fluid other than water, you'll need to use the correct density for that fluid. For example, oil or air would have different densities which would affect the velocity and the required orifice size. Always check the properties of the fluid you're working with. Temperature can affect the density and viscosity of water, which in turn can influence flow calculations. For most room temperature applications, 998 kg/m3 is a good estimate, but for high-precision or high-temperature systems, always use the most accurate data available. Orifices are a simple and cost-effective way to control flow in a system. They're easy to install, require little maintenance, and can be precisely sized for specific applications. Understanding how to calculate their size is a valuable skill for engineers and technicians alike. While orifice plates are useful, they do have limitations. They can cause significant pressure drops and may not be suitable for fluids with solids or debris, as these can clog the opening. Always consider the specific requirements and constraints of your system when choosing a flow control method. Suppose you're designing a water supply system for a building and need to ensure a certain flow rate at a specific pressure. Using the steps we've covered, you can calculate the exact orifice size required, ensuring the system performs as intended and meets safety standards. In engineering, it's common to round calculated values to standard sizes for ease of manufacturing and installation. In our example, the calculated diameter was 59.6 m, which we rounded to 60 m. Always check if standard sizes are available before specifying custom dimensions. When designing orifice plates, consider safety factors such as the strength of the plate material, potential for clogging, and accessibility for maintenance. Proper design ensures reliable operation and minimizes the risk of system failures. Thanks for joining this walkthrough on orifice sizing. We hope you found the step-by-step approach helpful and that you feel more confident tackling similar engineering problems in the future. Keep practicing and remember, clear calculations lead to reliable results.